a slightly different problem, right? You're given the solubility of lead to bromide in water, and you're asked to determine what the KSP is, the equilibrium constant is. So any ideas? Where do we start? Where do we start? Write the equation. Right, so we have our EBR2, EB2 plus 2 moles of bromide ions. Solids left out of our equilibrium expression, S2S. But you're told what solubility is. Molar solubility is how much dissolves, how many moles, how much of it dissolves per liter. So if X is equal to 1.05 times 10 to the minus 2 molar, you can plug these numbers in here, correct? Yes, Professor? 2 times S is 0.1 times 10 to the minus 2. K, our equilibrium constant, KSP, is equal to the concentration of N2 plus times the concentration of bromide squared. That's equal to 1.05 times 10 to the minus 2 times 2.1 times 10 to the minus 2 squared. What's our KSB here?
4.630
Times 10 to the negative 6. Now, does this answer make sense? Based on your knowledge of solubility product, equilibrium constant for barely soluble salts. What does K tell us?
whether it favors the product or the reaction.
It gives you the extent of your reaction. K needs to be very small for a barely soluble salt, telling us that we have at equilibrium a reactant favored reaction. Alright, so now we're going to move on to talk about effect of common ion on solubility. Chatelier's principle. Remember that term? What's that? The Chatelier's principle.
Oh, adding something to one side will cause it to shift to the other side.
The reaction is at equilibrium. Who wants to help her out?
The reaction is at equilibrium and some sort of change distance if it shifts the direction to resist the change.
To resist, to minimize that disturbance. So now let's say we had lead to bromide, right? And we've added that to water. And we're at equilibrium. So this is our solubility, right? 1.05 times 10 to the minus 2 molar. Moles per liter is dissolved in water, right? And let's say, for example, we add sodium bromide, a solution of sodium bromide to this mixture. What do you think would happen? So this is sodium bromide, right? Soluble or insoluble salt? Soluble. All group 1 containing compounds are soluble. All bromides are soluble except when bonded to silver, lead, or mercury. You guys will remember these. Okay, alright, so we have sodium ions and we have bromide ions. We add sodium bromide, a solution. You okay, Scott?
I'm great.
Okay, we add a solution of sodium bromide to our mixture here. What's common bromide ions. So essentially, we're adding more of our bromide ions to this mixture. What happens according to the Chatier's principle?
Shift what?
It will shift left. Whenever you add a substance that's in your equilibrium, it will shift away from the added substance. So what happens to the solubility, do you guys think?
Decrease.
It decreases. So adding a common ion decreases the solubility of the very soluble salt solution. So the same idea here. You have your lead 2 chloride, and if you were to add this to, if you were to add sodium chloride to that solution, chloride is going to be your common ion. Your equilibrium position is going to shift to the left, and then you're decreasing the solubility of your already very soluble salt. All right, so this is where you guys are going to pair up or get into groups of 3. We're going to determine the concentration of silver ions in seawater that has a chloride ion concentration of 0.55 molar. So you are going to have silver chloride, write the equilibrium expression for that. And then you're placing silver chloride not in pure water, but just in seawater that already has chloride ions in it. So actually I want you guys to do 2 things. You've already done the first one. Do you guys still have the solubility of silver chloride in pure water? That was the first problem we did. What was it? Remind yourselves. Come again? 1.33 times 10 to the negative 5 molar. You guys remember that? Okay, now we're putting silver chloride instead in seawater that already has chloride ions. We just talked about the effect of common ion on solubility. So solubility should decrease. So you should have a molar solubility less than 1.33 times 10 to the minus 5. Go! You're on the clock. What are we doing over here, guys?
Yeah, you can use that.
3.2,
Oh, you're done?
I think.
Let me see. So here, so at equilibrium, zoom in on this. So this is not your equilibrium conditions. You need to write out. Let's start here. So initial, your ice table. So initial. Yep. So solids are left out.
Yeah.
So blank, blank, blank. Okay. Initially you have no silver ions and you have 0.55 molar chloride ions. So change is going to be
Plus S.
plus S
And plus S.
plus S. At equilibrium you have no 0.55 plus S.
Oh yeah, you're right.
And then now you're gonna plug these in over here
Oh, okay.
and solve for S, which is a concentration of silver ions. How are we doing? So what? Huh?
I don't want to do it on the board, but I have the answer.
You have the answer. So why don't you want to do it on the board? You have the correct answer.
Oh, no, thank you.
No, thank you. Anybody? Huh? If I can check. Yeah. Two significant figures would be good enough.
Okay.
But absolutely. Do you want to do it on the board? Yeah, sure. Come on.
The backboard or in the front?
Right. Erase it.